And guys, today we are going to talk about NumPy. NumPy is a powerful open source Python library used for scientific computation and data analytics. NumPy stands for Numerical Python. It is a multi-dimension array library as well as a collection of mathematical functions to operate on. These arrays can handle large amount of data and are efficient in both time and space as compared to Python list. NumPy is also free and open source, making it a popular choice among data scientists and researchers. NumPy is also the basis of many popular libraries such as pandas, matplotlib, etc. These libraries seamlessly interface with NumPy, making it a versatile tool for analytics and visualization. Now, let's look at some code. We will start by importing the library using import. We will check the version of the library using the version attribute. We are currently using the version 1.21.6. There are multiple ways to create NumPy arrays. One way is to pass Python list or tuples in array method. By passing nested list or tuples, we can make array of multi-dimension. This method returns an ND array object, which tells us that it is a NumPy array. The object has multiple properties such as size, which tells the number of elements, ndim, which tells the number of dimensions, and shape, which shows the arrangement of elements. Here, the size is 6 as we have 6 elements in the array. We have a 2D array, so ndim is 2. The elements are arranged in 2 rows and 3 columns, so the shape is 2, 3. Other ways to create NumPy arrays is to use method provided by the library. It is usually the go-to method while working with large number of values. Let's explore some of those methods. For one dimension array, we will look at arange and line space. The arange method generates numbers between a range. You can also provide step as the third argument to skip values. Here we generated an array of even positive integers between 2 and 100. The line space method generates numbers which are evenly spaced between the range provided. Here we generated 10 numbers between 0 and 1. For multi-dimension, we have the full method which will generate an array based on the shape and element provided. The zero method which will generate an array of zeros of the given shape. There are also some methods specifically for generating two-dimension arrays or matrices such as diag method, which generates a diagonal matrix based on the values provided, and the identity method which generates an identity matrix and takes shape as input. Indexing and slicing of one-dimension array have same syntax as Python list. All forms of positive and negative indexing works and behaves similar to Python list. To extend it to multi-dimension, we have two ways to address the array. One way is as you would address nested Python list, where each bracket corresponds to each dimension. The second way is to use comma in the same bracket to represent the next dimension. Both works similarly. For example, here we are addressing first and second row and extracting the last element using the negative indexing. NumPy arrays can be rearranged in different orientation using the reshape method. Reshape takes shape as input. Here we are reshaping a one-dimension array of 18 elements and reshaping it into a matrix of 2, 9. You can also use -1 to infer the value of shape automatically. Here, NumPy inferred the value as 3 for the first dimension. Arrays can be concatenated using the concatenate method. It takes a tuple of NumPy arrays and the axis of concatenation. Axis is important if you are concatenating arrays with more than one dimension. As you can see in the examples, the result will vary based on the axis chosen. Other than those, we have hstack and vstack that solves the similar purpose of concatenation. We can also split arrays using the split method. It takes a NumPy array and the number of sections of split. In this example, we divided our array into equal parts of 2 elements each. This method also takes indices of array if splits of different shapes are required. Operations on NumPy arrays are all vectorized. It means that there is no requirement to write explicit loops. All the mathematical operations can be used as it is, and NumPy will handle the rest. But we have to make sure that two arrays are compatible for the operations to work. Luckily, NumPy handles the complexity for us, and it is termed as broadcasting. It is a set of rules which governs how shape of array are handled during operations. The basic idea to check if two arrays are compatible are either both arrays are of same length or one of the array has size of 1. Let us look at some examples. In the first example, we are adding 5 to an array. NumPy will broadcast that 5 and add it to the whole array element wise. In the second example, we are working with arrays of different dimensions, but since the first dimension is the same for both arrays, they are compatible. The first array will be broadcasted along the second dimension of the second array and we will get the result. You can try different array shapes to check whether some are compatible or not. NumPy has a lot of built-in mathematical functions to work on statistics, linear algebra, and Fourier transformations. Here we are looking at methods to calculate sum, mean, standard deviation, and variance, which are widely used summary measures in data science and analytics. Let's look at some methods for linear algebra. The dot and cross methods are used to calculate dot and cross products respectively. The names are very intuitive and easy to interpret. Some methods we are using are DET for calculating determinant, matrix rank for calculating rank of the matrix, INV for inverse, and EIGH for calculating values and vectors of the matrix. Now, what if the function you want is not available in NumPy, or you want to make a custom function and use it with NumPy arrays? For this, NumPy provides the vectorize method, which will generate a vectorized version of your custom method. Here, I have made a function which multiplies the value by 2 if the number is even, else multiply the number by 3. We can generate a vectorized version of this method using the vectorized method. The function will now work seamlessly with NumPy arrays. This concludes the basics of NumPy. Thanks for watching. Please like and subscribe if you learned something.